Hello everyone, I'm Tara Eloisavan Gulbeke, and the next two topics we will talk about are the major water quality factors that affect aquaculture animals, which are the dissolved oxygen and the pH. So first, we will discuss dissolved oxygen or DO. So what is dissolved oxygen? Dissolved oxygen is a measure of how much oxygen is dissolved in the water. In simple terms, it is the amount of oxygen available to living aquatic organisms. Dissolved oxygen is the gas of greatest importance in fish culture. It is a highly critical water quality parameter in fish culture. Air contains approximately 21% oxygen, but the amount present in water is quite low. Due to the low solubility of oxygen in water, it is important for the fish culturist to fully acquaint himself with the dynamics of DO concentrations. In ponds used for aquaculture, the major source of oxygen is the photosynthesis of phytoplankton. What is phytoplankton? Phytoplankton are tiny plants that produce the green color in many fish ponds. Dissolved oxygen in the water can be expressed in two ways. First, the absolute concentration, which is milligrams per liter or parts per million concentration, and second, the relative concentration, which is percent saturation. Ideal or desirable range of DO level for finfishes and crustaceans is 6 to 8 parts per million, or milligrams per liter, although 5 milligrams per liter is satisfactory. Reduced food consumption by fish occurs at DO concentration near 4 milligrams per liter, or parts per million. As mentioned before, dissolved oxygen is the gas of greatest importance in fish culture. So now, let's talk about what makes dissolved oxygen so important. First, let's talk about its uses. Dissolved oxygen is used for respiration. It helps in feed consumption, digestion, and assimilation. It maintains osmotic balance of fish, maintaining an internal balance of salt and water in a fish body. It helps in fish activities such as swimming, searching of food, and the like. It helps in the oxidation of metabolites in the aquatic environment, such as the ammonia and hydrogen sulfide into usable form nitrate and sulfate respectively. Now let's proceed to the factors that influence oxygen production in the water. Factors are as follows. Light availability. As light intensity increases, the more oxygen is produced, thus creating a favorable environment for more photosynthetic plankton, which results in more oxygen production. Next, magnitude of chlorophyll-bearing green plants, the concentration of nutrients, lastly, the temperature. Near freezing point and greater than 40 degrees Celsius is the temperature where plants cease to do photosynthetic activity. Oxygen holding capacity of water declines when it is warmed or its temperature is above optimum range. It is because high temperature reduces the solubility of oxygen in water. Warmer surface water requires less dissolved oxygen to reach 100% air saturation than in deeper, cooler water. Oxygen holding capacity of water declines when it becomes more saline. Seawater has a higher salinity, which is about 35 parts per thousand. The amount of dissolved oxygen is higher than in fresh water, which has 0 parts per thousand. Therefore, salt water has a lower capacity to hold oxygen than fresh water does, because salt water has less space for oxygen molecules due to the sodium and chloride ions it contains. Oxygen holding capacity of water declines when it is raised to higher altitude. This is because water holds less oxygen at higher altitudes. If DO reaches low levels, fish will show signs like the following: not eating and acting sluggish, gasping for air at the surface or surfacing, group near the water inflow, slow growth, and outbreaks of diseases and parasites. Management techniques in preventing problems with DO depletion. Monitoring DO at critical times at dawn down to 6 a.m., avoid overstocking, avoid overfeeding, sliding rule of feeding should be adopted, in example from higher to lower rate. avoid over-fertilization in the case of ponds, installing of aeration in the case of ponds, and keeping water circulation. Now that we're done with dissolved oxygen, let's now discuss pH. pH measures the degree of acidity or basicity or alkalinity of a solution. pH is a term used to express the hydrogen ion concentration of a certain fluid or solution like water. The P stands for power and H for hydrogen. Therefore, pH is the power of hydrogen. The hydrogen ion can be mathematically determined from pH values. pH indicates the ability of the solution to give up hydrogen ions as acidic solutions or to take up hydrogen ions as basic solutions. pH scale ranges from 0 to 14, 7 being the neutral. Less than 7 down to 0 as acidic, and greater than 7 up to 14 is basic or alkaline. The pH of natural waters is found to be high during the day and low at night. This variation is due to the large influence of concentration of carbon dioxide on the pH of aquatic systems. During the day, phytoplankton and other aquatic plants removes carbon dioxide for use in the photosynthesis faster than the respiration of all organisms return carbon dioxide to the water, resulting in the increase of pH. At night, photosynthesis stops and vegetal respiration occurs. Respiration continues to return carbon dioxide to the water. pH continues to fall in response to increasing carbon dioxide, and the pH shifts towards the acidic scale. It would be ideal to check the pH at daybreak and afternoon to get a profile of the diurnal shifts in pH. Water with pH values of about 6.5 to 9 at daybreak are best for fish production. Slow growth is observed in waters with pH values between 6 and 4, and death may occur at the pH values of 4 down to 0 and at pH 11 up to 14.